Okay, today we'll go ahead and talk about the test coming up tomorrow. Covers, well, all of what we've done so far. Chapter 1, again, more just the algebra review, will be probably having a little bit of that in there, calculating slopes or stuff like that, slopes through 2 points. But slope of the tangent line is more from chapter 3, chapter 2 and 3. But particular problems will come from stuff from chapter 2 and 3, not necessarily from chapter 1. But homework or the worksheets, if you have some to turn in, if you want to turn them in today, that's fine, but you can hang on to them. Either turn them in tomorrow or at the very latest Wednesday, and then make sure you finish all the online exercises on the Think Well, each of the sections, again by Wednesday. The test tomorrow, there will be 20 problems. And I do count each problem the same number of points. I count each one 5 points, and if I find the right answer, then you get 5 points for that. Any wrong answers, then I check your work. If you only have a wrong answer down and no work, then that's going to be -5. But if you've got some work down and maybe you miss a sign, those irritating little dashed lines kind of get to us, I'll give you 4 out of the 5 points, and the more mistakes, the more I count off. But show me some work, and even if you make a little mistake and get a wrong answer, you should get most of the points for that problem.
Do we have to use the same variable symbols that are on there?
Good question. As far as the variables, if the problem says what is the slope or what is the average velocity or instantaneous velocity, if you're going to end up with a single number, then the variable doesn't matter.
Okay. I was going to ask because I don't like to use t.
Yeah, and that's okay. But if it's find the derivative of the function in terms of a certain letter, then the answer needs to match with that letter. Usually if I do a problem like that, I'll put it in terms of x anyway, but we're so used to x, sometimes that's to our detriment. We need to recognize which variable we're using. Yeah.
Okay, so like in finding derivatives, like can we use like k or h instead
Yes.
of delta?
Yes, the derivative, the definition of the derivative notation, I don't care if you use the x plus delta x or x plus h. I think the Thinkwell material used both. Professor, what's his name? Berger uses the delta x, I believe, and then the guy who does the examples, I think, uses the h. So either of those. And I said earlier, if I see the right answer, then it's completely right, unless I specify, like use the definition of the derivative. Well, some of you already know the shortcuts. Function like x squared has a derivative of 2x. I'm not going to accept just 2x on that. You've got to go through the definition of the derivative. So that one is more, I guess the answer to the question is not just what is the derivative, but go through the process of the definition. So, but for the most part, I will be looking at just what's the correct answer. So, but I'll talk a little bit more about that as we go through details of section by section. So any other general questions about the test?
Are we gonna have things like about the squeeze theorem or anything on?
No squeeze theorem. That's a good homework and good kind of concept problem, but it's not a good test problem. We'll be kind of coming back to that later in the semester, and also Calc II and so forth, as kind of showing why some other things work out the way they do. But for this first test, no, we won't see anything like the squeeze theorem. Okay. And let's see, one other thing in general, I do not have a time limit. I don't make you turn it in at the end of the class period. So if you need extra time, you can have that. However, I will say, and this goes for the entire semester, I will not excuse you from being late to your next class. If you have a class like tomorrow would be 11:30 class, I will not excuse you for being late to your 11:30 class because you're working on your test. That'll be up to you. Is it worth your bettering your grade in here and possibly hurting your grade in your next class? Now, I'm trying to schedule all the tests on either Tuesday or Thursday. Most of you do not have classes right at 11:30 on those days. But there may be a time where we have to do a Monday, Wednesday, Friday. Many of you have 11:30 on Monday, Wednesday, Friday, but at least for now, I'm going to try to keep the tests on Tuesday and Thursday, so hopefully that won't be an issue. The test is designed so that you can get it done in an hour, but I know some students take their time and double check and triple check, which is a good thing, but it just takes that much more time. Okay. Well, the first types of problems that we'll have, find the limit. Now, we looked at a lot of different details on finding limits, but essentially it's going to be something like this. Might be something like I can make up a problem that will work. Sometimes that's kind of hard to do. And let's make that a plus. Okay. What would we do in something like this?
Plug it in to see.
Okay, plug it in. And what do we end up with here? Okay, 9 plus negative 3 minus 6. So numerator we get 0. Denominator we get 9 minus 18 plus 9. So we do get 0 over 0, as I tried to end up. So what do we do? Okay, factor. Top factors into what?
X
Plus 3 and minus 2. And denominator? Okay, plus 3 and plus 3. So what can we do with that? Okay, x plus 3 divided by x plus 3 is 1. We're left with x minus 2 over x plus 3, which now, go back to the original, plug it in, and what do we get? Negative 5 over, still get a 0 in the denominator, but at least it's not 0 over 0. What does this mean then? Okay. The limit does not exist, and I'm fine with you putting just D and E for that. But any number other than 0 in the numerator along with the 0 in the denominator, you get a do not exist, or the limit does not exist. Okay. This will be one type of evaluating a limit. Some other types, we may end up with the complex fraction. Let's see if I can remember how to do this. Set this up. Let's see. Yeah, what is it? 1 over x plus 1, and then minus 1 all over x. As we plug 0 in again, what do we end up with? Okay, again we get the 0 over 0. Now, in this case, to continue to do more work, there's actually a couple different ways to work through it. And one way, some of you have taken the numerator, combine it into a single fraction, which we can do that. This 1 would turn into what? Okay. Common denominator of x plus 1. So the numerator we multiply by x plus 1. Now we still have the all over x here. And one thing we got to be careful with, that negative is times the quantity of x plus 1. So we'd have 1. We'll go ahead and do a couple steps of algebra here. Minus x minus 1 all over x plus 1 all over x. And 1 minus 1. Okay. And we'll have negative x over x plus 1 divided by x, or multiplied by 1 over x. Then what can happen? Okay, the x's cancel out, and we're left with negative 1 over x plus 1. And then finally, we do the calculus part of it. As x approaches 0, we end up with what? Okay, so that limit value would be negative 1. Now, that is a valid way to do this problem, but some of you, from the very beginning, work it out a little differently, and we'll just look at the complex fraction part. From the beginning, instead of turning the numerator into just one single fraction like we do here, we could eliminate the fractions by multiplying the overall numerator and the overall denominator by that least common denominator of x plus 1. And in doing that, well, x plus 1 times this fraction, the x plus 1's cancel, leaving 1 for that first term. But then this second part, minus 1 times this quantity, and then all over x times the x plus 1. Well, this is where we would multiply the negative 1 through. And we're kind of to this point after multiplying the reciprocal. So either direction, doesn't matter to me which direction you prefer. You should get to the same point either way, and ultimately get down to the limit value equaling negative 1. Okay? Questions there? Okay. Now, in the last worksheet, the derivatives of special functions, we saw this form one more time when we were taking the derivative of, say, 1 over x or 1 over x minus 2 or something like that. So hopefully that reviewed some of those operations for you that we did early. Okay. One more type of limit that we evaluated deals with the square root. So a limit in this form, again, what do we end up with when we plug in 2 for x? 0 over 0, which tells us we've got some more work to do. Now, what if it does not turn out to be 0 over 0?
That's the answer.
Okay, then that would be the answer. So make sure you do that first thing. Most of these will have some work to do, but there might be one or two that actually equals that nice little number. But 0 over 0, we've got some more work to do. And in this case, what do we need to do?
Use the conjugate.
Okay. Multiply top and bottom by the conjugate of the square root on the top, square root of x plus 4 plus square root of 6. Now we do want to multiply out the numerator, but don't multiply out the denominator. You'll see why in a second. Leave this as x minus 2 factor and then the square root factor. But as we multiply out the numerator, first square root times itself, we'll just get the x plus 4. Then the reason we multiply by the conjugate, the square root of x plus 4 plus the square root of 6, or not plus, times the positive square root of 6, and then those square roots times the negative. Those middle terms cancel each other out because of the opposite signs. And then finally, the last part, we end up with negative 6. And finally, the numerator turns out to be what? The x minus 2, and we'll be able to cancel that with the x minus 2 factor in the denominator. And finally, we go back to our limit. We have just the 1 left over. Don't forget, even though we cancel everything out, there's still a 1 left in the numerator. And square root of x plus 4 plus the square root of 6. Plug in 2, and we get we'll get square root of 6 plus another square root of 6, or 1 over 2 square root of 6. And as far as what form should we leave it in, that's fine with me. Some textbooks would go ahead and change it to rationalizing the denominator, but in calculus, we usually want the denominator to remain with the square root. So that is plenty good there. Questions? Now, we also looked at calculating limits based on a graph, and then we kind of extended that idea with continuity and so forth. But let's first look at a graph of something. Now, in this case, let's see what the limit as x approaches negative 2. What's that little negative sign up there mean? Okay, from the left, x approaching negative, let's not go -2. How about -1? Oh my word. Don't need quite that big of an eraser. Okay, how about -1? Here we go. -1 from the left, this would equal what? Okay, it would equal 1. As we come in from the left, we're getting closer and closer to the value of 1. Guess we need that. What about the limit as x approaches -1 from the right? Okay, it's going to be -1. So what's that tell us about the limit as x approaches -1? Okay, it does not exist. From one side it goes to one value, the other side it goes to a different value. For it to exist, it has to go to the same value. Now, what about the limit as x approaches 3? Okay. That is going to be 2. From the left, we're approaching 2. From the right, we're approaching 2. Now, whether we have an open circle there or a solid dot, does that affect the limit? Okay, no. We do have a solid dot there, but even if there was an open circle, the limit would be 2. Since there's a solid dot there, we can also say what about x equals 3? We can say f of x is continuous at x equals 3 because, well, first of all, the function value is defined. We could say f of 3 is equal to 2 because of the solid dot.
Can we write it as that instead of the function is continuous at 3?
It will depend on how the problem is worded. I will, in the continuity problem, I'll probably say what x values is the function discontinuous. So in this case, we wouldn't be messing with x equals 3. It's a possibility for discontinuity because of the way the graphs are, but where we have the solid dot right on where the two graphs meet, then we have continuity. But f of 3 would equal 2. The limit also exists at that point, and our condition 3, as I listed them out on the worksheet, the limit equals the function value at that. So we do have continuity at x equals 3. Where do we not have continuity? Okay. At x equals -1, we have the situation of a jump discontinuity. The limit does not exist, so f is not continuous at x equals -1. Now, what situation would we have removable discontinuity?
If there was an open circle where 3 is.
Okay, open circle here instead of the solid dot, then we would have discontinuity at x equals 3, and it would be the removable. Okay, but any jump, any asymptote at a certain x value, then it's non-removable, or a little less formal, the jump discontinuity. Okay, So we'll have some limits from a graph, but then we'll kind of extend that idea with continuity. Make sure you understand that. And as we move into the idea of continuous or discontinuous, there's going to be some functions, not the graph, but the equation of the function. Where is this function discontinuous? And if discontinuity, then is it removable? Is it non-removable? Okay. Now, some of those will be a particular function. Such as the limit we talked about earlier, and actually is that. And in this case, well, this was kind of a, let's see, let's actually flip that around. We'll put x squared plus 6x plus 9 on top. And x squared plus x minus 6 on the bottom. X, not x squared, but x. And it's not going to let me do that. Imagine that's erased. I don't know why it doesn't let me go back and erase that, but so where would this function be continuous? Where is it not continuous? I guess the question would be, where is it not continuous? And again, factor not continuous at what x values? Okay, not continuous at -3 and at 2. And then which one of these, if any, would be removable?
I'm gonna say 2.
Okay, actually the -3, because we can cancel out the x plus 3. At -2, we'll actually have a vertical asymptote. But at -3, we'll have a hole in the graph, so this is the removable one. And in Unit 3, I think Chapter 8, we'll get into a little more of the details of graphing with asymptotes and holes in the graph and so forth. But this kind of leading up to that. Okay, question there? Now, the other type of where is it discontinuous might involve a piecewise defined function, and that's basically where the split is between the two parts. Just got to make sure if it's not continuous, then the limit cannot equal the function value. You can go through the steps there on figuring that out, but it's basically, does the one side match up with the other side, and is the function defined at that point as well? So, limits, continuity, any questions so far on those types of problems?
How did you know it was removed?
At -3, we actually end up with that part of it getting canceled out, which the x minus 2 gives us our vertical asymptote at x equals 2, but there's no x plus 3 left, so that's where we end up with the hole in the graph. Okay. After our continuity, we've got back into calculating average and instantaneous velocity. Instantaneous. That's too big of a word. Now, average velocity, remember that's the change in distance over change in time, or if we're looking at position function, we use P for part of that. Sometimes we use S for a position. Maybe average velocity from 3 to 3.5 seconds, something like that. We'd have to calculate the distance that it traveled in that time period. So P of 3.5 minus P of 3, and then divided by the change in time, the half second that it changed. Now that would be our average velocity. Also, this form, this operation is used to find the slope of a secant line from one point to another point, except it would be usually in terms of f of x. So f of 3.5 minus f of 3 all over 3.5 minus 3. So this form, anytime we're given or asked to find the slope of a secant line, average velocity, average speed, I think that was the main ones we looked at. And then if we're asked to find the instantaneous velocity, how does this problem change? Our instantaneous velocity, we'll say at t equal 2, but could be at any t value. That gets into working with our definition of the derivative as we now know it. Back then we didn't really know that was the operation we're dealing with. But and again, some of you figured out, well, we don't really need to put in the 2 right now. You could find the derivative, and you could even use delta x if you want, or you could use h if you want. But we'll go ahead and change the formula. Now, if you change over to x, make sure everything gets changed to x, so everything cancels out the way we need it to. And this problem, just a huge algebra problem, and then at the very end we do a little bit of calculus, plug in the 0 for delta x or delta t, and so we end up with the derivative, and maybe that's something like 2x minus 5, whatever that will vary greatly depending on what the function is, but something like that. Then plug in your derivative value or your time value, and the way we could answer this, the instantaneous velocity at 2 seconds would be -1, and on velocity problems I will most likely give you units, probably feet and seconds. So the instantaneous velocity would be -1 foot per second. Why would it turn out to be negative?
Because it went backwards.
Okay, it's going in a certain direction. Vertical motion, negative direction, means it's going down. Horizontal motion, which we looked at a little bit at the end, means it would be going to the left. So velocity can be negative. So we've kind of did a lot with this equation, and leading up to that, before we add the limit, the average velocity, slope of the tangent line, and so forth. So then we got specific with the terminology of the derivative, the operation of the derivative, and find the instantaneous rate of change, a little more general term there rather than instantaneous velocity, but it's still find the derivative and plug in your x value or t value, whatever it may be. Slope of the tangent line, again, find your derivative. And then on the derivative, that worksheet, we did use the definition of the derivative to find the derivative of the function. I will have at least one of those on there where you do have to go through the limit, the definition, and go through all the algebra, make sure you don't lose any negative signs and all that good stuff, and then take your limit as delta x approaches 0. Make sure you show that part at least at the end. Whether you attach the limit every step of the algebra, I don't care about that, but make sure you attach the limit as delta x approaches 0 at the very end so you can show why delta x goes away. And then after we did that operation, looked at it as instantaneous rate of change, instantaneous velocity, slope of the tangent line, then using the derivative, okay, we did more of the same. Motion of an object, look at how we use the derivative for describing the motion horizontally, okay, and I will have you sketch a graph on the number line, so do your little where it starts, which direction it goes when it starts, when it stops and turns around. Where will an object stop?
When it's at 0.
When what's at 0?
The time velocity.
Okay, when the velocity equals 0, when the derivative equals 0. And that will give you the time when it stops. Then you got to go back to the position function and find out where it stops, not just when, but where it stops. And then keep going from there. So it may only stop in one place, it may stop in 2 places, or even 3. So, and then derivatives of special functions, make sure you know that. I guess we talked about horizontal and vertical motion. We talked a lot earlier about vertical motion. If something is shot upwards, when will it stop? How long does it take to fall? All that good stuff. And then this last worksheet with the derivatives of your rational functions and the radicals. Functions. So that, I think, is pretty well all of the different types of problems that will show up. So, any particular questions? As far as tomorrow goes, if you want to start the test early, I will be down in room 101 from 9:30 to 10:20, and then at 10:30 I'll be up here. So if you want to start early, come down there. I'm in Calc 3. I've got them working problems as well, so don't be afraid to walk in, and you're not going to be interrupting class. But if you want to make sure you have plenty of time to get done by 11:30, that's fine. Okay. Don't forget, homework, You can hang on to those, turn them in tomorrow or Wednesday. Make sure you get all your online exercises done as well.